Hello, everybody, and welcome. I'm very happy and very excited about today's showcase. A very interesting topic and a very interesting project to go along with it. My name is Flavio Popescu. I am a structural engineer at Strusoft Denmark. Today, I am joined by my colleague, Stoyan Lumilan, technical expert from Strusoft Estonia, and our special guest, Eloi Duran, from Eckersley O'Callaghan at UK. Today we will be using the GoToWebinar platform. You can see the questions field in your GoToWebinar window. Please type in any questions you have during our presentation, and we will do our best to answer them. Today's topic is timber in general. Of course, we will focus on CLT panels and a very interesting project, the Atlassian Tower in Sydney, Australia. I will allow our guest Eloi Duran to speak more about that. But we will start with some CLT panel theory in femdesign. And even before that, I would like to make a small introduction about Strusoft and who we are, what we do, even though today we will focus on femdesign. We do develop and distribute several software. WinStatic for individual element calculation and design, including frames. BIM Energy for energy calculation and optimization in buildings. Impact Precast and Impact Reinforcement for factories which produce prefabricated concrete elements. And Prestress for pre-stressed concrete element calculation and design. We are a leading distributor and software developer in Scandinavia for structural design software. You can see here a rendition of our users across Europe and Northern Africa and a little bit of Asia. You can see a lot of users in Scandinavia, the Nordic countries. We are a leading software provider here, and we have users across Europe, in the UK as well, and around Central and Southern Europe. We have offices around the world. Our headquarters is in Sweden, and we have 3 offices there. We also have 3 offices in Denmark. Our most recent office in Finland, and we have also branches in Romania, Hungary, and in Asia, in the Philippines and India. Let's talk a little bit about femdesign, our focus for today. Femdesign is our 3D finite element method software for modeling, calculation, and design of structural elements. You can do a lot in femdesign. I will present a few major topics today. You can model any type of shape, really, in femdesign. You can import DWG drawings and start building from the ground up. You can also import 3D drawings and start modeling as shells and calculate stresses in those shells and deformations. As I said, you can basically model any type of shape and structure in femdesign and calculate the stresses in those shells. A very powerful tool is the crack-section analysis for concrete design. You can calculate a concrete slab with reinforcement in it and study the long-term effects like cracks. You can perform a crack-section analysis and investigate the cracks in an iterative procedure. Once the crack is located, the stiffness is reduced, and then the loading continues until the next crack, and so on and so forth. FemDesign has design modules. One of these is the steel design modules. You can perform a detailed calculation and verification according to Eurocode on steel elements and get the detailed report with the detailed calculations, which is ready to be printed and added to the documentation. Concrete design, which allows for design of concrete beams and concrete slabs. You can also obtain a detailed report of the calculations and the reinforcement design in beams and slabs. And also there is a timber module, which we will actually talk about a bit more today. Similarly to concrete and steel, you can obtain a detailed calculation and verification and perform a design on your timber elements, including CLT panels. We will talk a little more about that in a second. FemDesign also includes a 3D soil module. This is an advanced 3D finite element model, and you can study the deformation and the forces in these 3D elements, which is a more accurate representation and behavior of the soil, as opposed to a spring model here and a bedding modulus. You would get a much more realistic of the behavior of the soil, and basically we can model starting from the soil, the infrastructure, and the superstructure all in one model. That is the power of this 3D soil module. I gave you an overview of what you can do in FemDesign. Of course, there's a lot more, but right now, let's jump into our main topic of today, which is the timber module. For that, I will hand over the presentation to my colleague, Stoyan. Hi, Stoyan.
Hello, everybody. Can you hear me nice and well?
Yeah. Yes, very well.
That's good. My name is Stoyan. I'm technical support, technical expert and consultant from Estonia. And today I'm going to talk about the CLT. I'm just going to wrap it up really quick. I'm talking about the theory part. Don't worry, it's not going to be very in-depth. If you want more in-depth theory, then you can always read the manual. I will show how you can access it later. Also, I'm going to show a little example based on orthotropic versus laminated shells, so you can understand better what's going on in the CLT world. And also talking about stresses, how easy it is in FemDesign to get the maximum stresses or to look at the maximum stresses, and also do the CLT design. So we are looking at those options in FemDesign as well. So let's start with the theory. The reason why we need to talk about theory is that there are some limitations in Eurocode 5. Mainly, the CLT is not individual material yet. We need to take some other steps how to calculate it. Also, Eurocode suggests beam theory, which would be too simplified for FEM design, because we would like to use the arbitrary shapes, not only the beam shape element. There are some other methods available also in some handbooks, but most of them are either too limited or too simplified to be used in FEM design. So we need to figure out how to go around this problem and implement something new or different. And we chose the laminated shell theory. It is also called equivalent single layer method in some literature. So if you see that name, then you know that it's the same thing. It is useful in general to check the deformations and stress distribution layer by layer in composite shell. And that's exactly what the CLT is, a composite element. The advantage of this method is that with slightly longer calculation time for element stiffness matrix using the homogenization procedure, same number of equations remain in the final structural equation system, regardless of the number of layers. So even if you make really strange shapes with thousands of layers, in the end, your final equation system for the whole structure will still have the same number of equations. So it saves a little bit time in the end. Another advantage is that we can actually model arbitrary geometry, as I said before. We can also take into consideration different boundary conditions. We can make the whole structure with shells and bar elements, because the degrees of freedom of the CLT is compatible with the other elements that we have in FEM design. So you can use everything in the same model. You don't have to break it down into CLT model and then beam and regular orthotropic plate model. We needed to implement the new finite element formulation, and this takes into account this coupling effect, the special effect, which is the action or interaction between membrane elements. The laminated composite shell in FEM design uses first order shear deformation shell theory, also known as Mitlin-Reisner. We use the same actually for the orthotropic shells as well. So it's not the first time that we use it. It is important for deflections because contribution of shear deformation can be significant, especially in moderately thick shells, and especially so in laminated composite shells that we have. In CLT, there is greater role of transverse shear stiffness that has to be taken into account. Okay, let's move on. In CLT, it's mostly the rolling shear that we need to consider or not lose, keep in our minds. Also, we should think about the geometrical limitations of the panels. We have suggested a geometrical limitation of 1 to 10% of the length of the element. So the thickness of the panel should be 1 to 10% of the length. And this is not a critical limit, but it's more like a good rule of thumb that you can use. So even if you're a little bit below or a little bit bigger, then it's no problem, but try to aim in the middle. Okay, This is of course well-known formulation of the stiffness matrix and force vector, and also the strain vector. So in the left side, I hope you can see my mouse. In the left side, we have the force vector with the moments, bending moments, and the normal forces and the shear forces. In the middle, we have the stiffness matrix with the bending part, bending stiffness, the membrane stiffness, and the shear stiffness. And in the right-hand side, we have the strain vector with the curvatures, the mid-plane strains, and the shear strains as well. But the special part of this formulation or this formula is that now we have included those B parts, which are the coupling effect parts. For the regular autotropic plate, we don't have those parts, so they are 0. But for CLT panel, we implemented this new formulation, so we need to have this coupling effect here. That's what is making the formulation special. And the stiffness matrix itself, it's the same size as all the other elements. So like I said before, the laminated shells are totally compatible with other elements in FEM-design. Okay. Let's see the first example. It's orthotropic versus laminated shell. A little fight between those two. Let's see how they handle in FEM-design. I have modeled two different files. Actually, this one is for the orthotropic plates. Let's see the parameters first, or properties first. I just selected a random orthotropic shell. You can see from the drop-down list that it's orthotropic shell, and just a random type. I actually made it myself to be more similar to the CLT panels regarding the stiffness. For stiffness, we have a new button down there. Actually, you can see the stiffness of that element. You will see all the parts of the same stiffness matrix. So you will see the D part here. If I'm looking back at the slide, the D part, upper left-hand side, and also the A part of the membrane stiffness and the shear stiffness. And you can even see the B part, or the new coupling effect, but you can see it's all 0, because for the orthotropic shells, this must be 0. There is no coupling effect in orthotropic plates. And if we load those plates with a force, in-plane force, then you can imagine what we get. Of course, we get in-plane deformation. It's quite usual and expected. Nothing special here. I modeled two plates because they have the different grain direction, but it doesn't matter much in my scenario. But if we are looking at CLT, let's open up the other one. Yep, the CLT plates. They are now cross-laminated timber, not orthotropic shell anymore. And again, I defined just a random one. I will show the details later, but just for now, you can see the stiffness matrix as well with all the parts. But now you can see that the coupling part has actually some values in it, so it's not 0 anymore. So there must be some coupling effect going on. And if you analyze this using the same kind of in-plane force, then you will get this behavior. So now the plates are acting totally different because there is basically out of plane deformation happening between the layers that is making those plates nice like this. All right. Regarding the structure or the properties of the element, we can see what we have, what we can change. You either modify the existing ones or create new ones. I will just modify it just to show you. we have this new dialog consisting of all the layers of the CLT. Right now I have this only 2 layers CLT, but you can add as much layers as you need. Just click on the empty space and you can select the material for that layer. So it's the regular Timber library that we have inside Vendesign. You can change the thickness, of course, for each layer. Let's say I want to make it really thick, the first layer, and the lower layer is still thin. If I hover over the picture with the mouse, I can see that in the upper part in the chart or in the graph or spreadsheet, it will highlight the line with the yellow color, so you can easily identify which layer it is that you are looking at right now. And of course, you can change other parameters like the angle of the elements. So it's up to you what you want to use. And you can of course fill in all the value here as well, all the YAML modules and other parts. But if you're adding a new layer, I'm just randomly selecting something from the list, it will actually automatically fill it in for you. So it will take the same data that is in the database and just fill it in. Of course, you can manually change it if you want to change something, like you can just modify that value and you're good to go. And deleting is just selecting the element and pressing delete button. So it's really simple. Also, you have the service class deformation factors here for each of the service class. So you can change those if you like. I'm just going to show you what happens if I'm changing them. And you have stiffness reduction factors as well. Those are the factors that you get from the manufacturer, for example. So if you are looking at the values here, the R33, it is the same value. Let me see, just a second. Yeah, I closed the picture. Unfortunately, I'm not going to search for it, but it will affect the stiffness matrix. It's actually a factor right in front of those values. You can have the deep in-depth look if you are looking at the manual. So there is everything written down regarding all the references to where it comes from. But you can reduce the stiffness basically using those factors. So they are just the reduction factors. Also some information down here, the total thickness of the plate, which isn't updated yet because it's not supposed to be 45 because I changed it back, but it will update as soon as I press OK. So you will get the right values here. And also the total surface mass or weight. Okay. Another part that you would like to see is that we actually have the limit stresses here as well, not only the mechanical properties. So for each layer, you can see all of those strengths, material strengths. And I actually have also a picture here just to help you out if you don't remember or just to follow this example. We have all of those values that are listed here on this picture shown. So if you just take one plank out of this CLT, out of this one layer, you have those bending strengths, perpendicular and along the grain. You also have the tensile strength, perpendicular and again along the grain. You have the compression strength the same way. Then you have the in-plane shear strength, transverse shear strength. Then you have the rolling shear, which is special for the CLT. And you also have torsional strength at load contact surface. So it's all of those values that you can change or modify for the element. You have them also in PEM design, so you can change whichever you like. But for now, I just accept those properties as they are. Press OK. It's just a notification. I have two different materials now because I changed some parameters, mainly the KDF values. But if you are looking at the KDF values now, I can select the service class and it will actually automatically update the KDF for each one of the serviceability limit state. But I can, of course, manually change them as well if I so choose. So I can place something different here as well. Of course, the regular factors, the material safety factor, gamma M, and system factor cases, they are all here. The cases actually could remain 1 because it's mainly necessary for a beam theory, but we are not using beam theory, so it doesn't affect us. We can just keep it 1. Okay. Also, of course, some other options down here to consider the shear coupling between layers. If we turn that off, we basically have just few plates on top of each other, not glued together. And we can also exclude the glue at the narrow sides. So we can exclude the glue that is between the blanks in the same layer. All of those, of course, affect our end results. Okay, let's see. Let's see some results as well. Let's look at the stresses, and then we will look at this design as well, but I will just open up another example. Just a quick one. Okay, here it is. It's just a random structure, but I wanted to make an arbitrary shape, so I made this Mickey Mouse picture here in the corner, just to show it's possible to calculate like this. PEM design doesn't mind. Also for the walls, we included holes. So arbitrary shapes can be defined and can be calculated and can be, of course, designed as well. But let's look at the results first. I wanted to show you the maximum stresses or the maximum results, maximum of load combinations. Right now, we actually have quite a few load combinations, 8 combinations in total. And we can see the maximum of all of those if we are just looking at the results and maximum of load combinations. And then let's look at the stresses, laminated shell stresses. It doesn't matter which one I take because I will go into the detailed view anyway, so you will see it in greater detail than just a colorful picture here. But I will just select the upper one, display it with the color palette. Maybe it's visually more pleasing. And then I will select the detailed result. In the detailed result, we can either select one point or select the whole laminated shell. So we have different options, but let's just go with the point at first. Okay. I selected, actually had a point. I will show you again. Actually have a point right in the middle. So I selected the same point. Okay. Here you can see quick view of the plate, also with my Mickey Mouse cutout. So that's really nice. You will see where the point actually is, the PT. And the PT is actually the closest finite element node. So you can see the information here, also a little bit information about the panel itself. And then you will see those stress results. Right now, I'm actually looking at the all components plus function. So what it means is that for that point that we selected, it will show me which load combination produced the maximum sigma x, which load combination produced the maximum sigma y, which produced tau xy, and so on. We can see it right here If you're looking closely, then this is from load combination 2. This is also from load combination 2. But for example, tau xz is from load combination 1, so it's not coming from the same load combination. And also this one is from the first load combination. So different load combinations produce different results in that point across all the layers that we had. We have 5 layers at the moment. But you have different options here as well. For example, you can select all layers sigma x, for example. And what this does is that it will find out where is the maximum sigma x in which load combination across all the layers. And then it will show us the results of the same load combination for the other stresses as well. So now everything belongs to the load combination 2. And there is even a third one, or third group, I would say, which is layer by layer approach. So we can, for example, select layer 4 and see which load combination produces the maximum sigma y minus, for example. Right now it's pretty boring because it's the same load combination. Let's see, maybe we have something different. It's load combination 2 or 1. It's either one of those two. So we don't have many combinations here for the ultimate limit state. Yeah. Anyway, layer tau xz and minus. So if we are looking at the xz layer 4, so the fourth layer is right here. It's a little bit bad to see at the screen, but you can follow it up if you want. Then it will just take the minimum tau xz and select the load combination and show the results of that same load combination for each of the stresses in that point, in that specific one point. But we have something else as well. We can look at the maximum of all of the points if we select the second option here. So we don't select one point, we just select the whole plate, and it will actually produce some relevant points on that plate. Right now it selected 5 different points, and we can select the same kind of results. So for example, all components plus, it will tell me that sigma x comes from load case 2 from point 1, sigma y comes from load case 2 but from point 2, and so on. So each one can be from different point, each one can be from the same point. You have many different options how you would like to present the results and use them for the design or just checking. And here we have the same options. We can select either all components, which might be different for each layer might be different for each load combination, or layers, or just one layer, whichever layer we want. This is pretty nice way to see the results. It's quick and easy and a really good overview. Okay. Yeah, now we move on to the design. I will talk about this picture really soon. First, I will check the design results. Then I will talk about this. I will go to the Timber design. We now have a new function for the CLT. It's CLT panel. So you can use that one to design the CLT panels. It's both for the plates and for the walls. So everything can be designed using the same option. And I've already run the design calculations, so we can just check it. And the utilization for the highest one is 72%, mainly because of the Mickey Mouse here in the corner. But let's say for this wall, it's of course much lower. But if you want to see more detailed results, then we can just query it using the magnifying glass as usual. And now we don't have to specify a specific point. We can just select the whole plate. It will again generate those interesting points and show us some panel properties here, which is really nice and tidy. And then, of course, comes the design checks that we have been looking for. Here you can see the error code reference. It's error code 5 and chapter 6.2.3. So you can follow it up if it's correct or not, if you want to hand calculate it as well. But for many of those checks, we actually need to separate the sigma for normal stress and the bending stress. So this is why this picture was here in the presentation. This is how we do it. We separate the sigma that we get from the analysis, and we separate it as the bending part on the right-hand side, and as the compression or tensile part. So we can, after the separation, we can use the same formulas that we have in Eurocode. And it's the regular Eurocode checks: tension and bending, compression and bending, shear, XY, and shear XC, and also shear YC. So those are all Eurocode checks. You can see from the reference. But in the bottom here, you actually see that there are some calculations that don't have any reference. Those are because we have extended the checks. We don't rely only on the Eurocode checks. We have added some additional ones. They are totally optional, so you can actually turn them off if you don't want to use them. But here is some conservative checks. If you want to turn them off, you can use this wrench icon and select the element and just uncheck the shear interaction formulas. So if you turn it off, for example, let's do that, and I will check the plate again and go to the detailed results. Then you will see that after the shear part, there is nothing. There are no checks anymore. So you can just turn them off if you don't like to use them, or turn them back on using the wrench icon again. So really very simple and easy way to do it. Okay. Just about those checks, let's see if I can show them here as well. Yep, I selected the wall now. So we have some more checks, but those 3 are here still. So the first one is checking the resultant shear stress in grain direction. The second one is relevant if there are rolling shear and tensile normal stress perpendicular to grain. And the third one here is rolling shear and compressive normal stress. Okay, and additionally, you can see that for the walls, you have something called buckling, so we can actually check it as well. It's again not exactly according to Eurocode because there is no obvious buckling check for CLT in Eurocode, and no other software, as we know it, uses this or even offers this functionality. So we might be the only one who does this, but it's again optional check. You can use it if you want. We followed the basic rules of Eurocode regarding the reduction factors for this to work. I will show you on the slides as well. We basically use this check to check the buckling, and the main idea behind it is that we need to find, or the main problem here is that we need to find a KC, reduction factor. And for this factor, it's the same formula here. To find the KC, we need to solve all of those equations, but it comes down to finding the beta C and also defining the buckling length beta. In FEM design, we can define all of those using the same wrench icon. If I'm selecting the wall, Here I can enter the beta C if I want to. So the 0.2 is like the default value for us. There's no specific value in your code for CLT. So we put 0.2 as a conservative estimate for it. Also, if you want to reduce the material properties, you can use the upper one here as well, the reduction factor. And this reduction factor should be between 0.67 and 0.84. We also place the 0.84 here as a default value. To define the buckling length or the buckling direction even, we have the other tool here called buckling length. You're not limited to defining the buckling only in the vertical and horizontal directions. You can actually define the buckling in arbitrary direction if you want. Nobody tells you that you have to do it, but then you have to, of course, select the user-defined option here. Then select the plate. It's a little bit difficult to select the plate if I have that visual style. But let's say I want to define the buckling in that direction. So now I can do it. Now I have the buckling here. And of course, I should define the buckling length as well. Let's put 0.7 here, for example. And if I calculate it now, or check it, and go to the detailed results and look at the wall, I can see that there is this buckling check now. And yeah, it's following the same rules as I showed on the slide. So we're doing it for each of the layers and getting the end result. All right. Yeah, I think we covered most of it, or the basic of it. If you want to know more, there's always a chance to go to TrueSoft webpage, or just Google Wiki FEM design. And here you have our online manual, and you have other manuals here on the left-hand side, where you can choose the cross-laminated composite shell theory, and you can read it, you can study it. There are all sorts of references for how this method was not invented, but why it was selected and what's the background, and also some verification examples. So if you want to follow along, this is a good place to start. Right. So I thank you for listening, and I gave the word back to Flavio, I guess.
Thank you, Stoyan. I'm just gonna move and pass on to the microphone to Eloi.
Oh, can you hear me?
Hi, Eloi. Yes.
Right. And can you see my screen as well?
Yes.
Brilliant. I'm also going to turn on my camera so you can put a face against it. Are you seeing my screen or are you seeing my face?
We see both. Oh, yes, we see both.
I've lost control over now. Good. All right. Hello, everyone. Thank you for that in-depth introduction to FEM design. I'm going to talk more about an application of the software and how we've used FEM design to help us with getting to schematic design of the Atlassian tower, at least for the CLT bits and the Glulam bits. So the Atlassian project is in Sydney. It's very central, right next to the central station you see on the right-hand side here. It's a 40-story tower with as much timber you can put in a tower of that height, pretty much. That's the goal expressed by the client, to try and reduce the embodied carbon footprint. And it's also the beginning of a new tech hub of that area of Sydney. So Atlassian are keen on they're going to be the first ones building a tower, and then as other tech companies will come in the area, there's going to be more towers just to the south of it. So this is a fresh start for a new hub in Sydney. So the client is Atlassian. They are a tech company which is pretty big in Australia, and they're famous for developing softwares that help software developers. So not something I've come across before in the past, but certainly a huge company there in Australia. The architects are called Shop. They're the lead architects. They're based in New York, and they're being helped by another company, a local company in Sydney called BVN. And for the structure, it's us in London, EOC, and we're also being helped by a company in Sydney called TTW. And we've also got a mission to design the facade, and that's done by our San Francisco office, by Lisa and her team. About the tower, so it's about 180 meters from the ground floor. It's not a simple structure at all. It doesn't touch the ground for the most part, but the central core that goes to the ground and to the foundation, and 2 big columns, but the rest is overhanging, if you like. The overall floor area is about 68,000 meters squared, and in this we want to squeeze as much timber as we can. And so at the moment, we're looking at about 8.3 thousand meter cube of CLT and 3.5 thousand cubic meter of glulam. The tower has a series of habitats, is how we call them. So every thick black line you see on that diagram is called a mega floor. It's a compartmentation for fire. And then the 3 stories above that, every time, are made of timber. We couldn't build a 40-story made entirely of timber, but having those fire breaks every 4 stories allows us to treat each of those habitats as individual separated spaces for fire. This is just a nice visual of the timber habitat seen from standing on the mega floor. And as you see, that the timber parts are completely detached from the main facade, creating that park space, and the timber overhangs over the park, but it doesn't use the external structure to support it. So it has a series of cantilevers on that side. And that's another rendering from the inside, showing, well, obviously a keen intention to express the timber and expose it as much as possible, having exposed services as well, running through beam penetrations, and exposed CLT soffits and glulam beams and columns. Just a bit more details on how the structure works. So the tower has a central concrete core in the middle, which is what you see on the first line here. And all the red elements on that diagram represent what we call the mega frame, or compartmentation floors, as they called them previously, or mega floors. They are the fire breaks. And then the 3 stories above that fire breaks are made of timber, which is what you see in sort of yellowish on the diagram. On some areas of the floors, we've got some large cantilevers, and we couldn't really just use glulam to achieve those cantilevers within a restricted depth. So we had to use some steel hangers, which take some of the load to the mega floor above the top timber floor. And finally, the pink elements forming a digrid, or an exoskeleton, as we call it. These are forming the primary structure. They're not really related to any of the CLT design, but certainly a key inspiration from the architect and a key structural element. I'm not going to talk about these more today. This is a section through a typical timber habitat. It's probably a little easier to understand how things are articulated together, but in red again is the mega floor, and then you've got 3 stories of timber with those service penetrations running through the beams. And you can see maybe even better now what I meant about large cantilevers over cantilevers, and the top floor on the top left-hand side of the image being hung from the mega floor above. On the other side, on the right-hand side of the core, is a more regular framing, but you can see some challenges here where you have beams cantilevering and then the CLT floor cantilevering even further and going around the exoskeleton. Right, so we've used FEM Design TrueSoft for all of the timber design up until now, and it's been really useful and has allowed us to do checks that we wouldn't be able to do on simple, I guess, span to depth tables or easy softwares you can find for free online. A lot of things that Stoyan mentioned today have been used. So some of the challenges we've had, which I've sort of illustrated in this slide, we have some curved corners around the south. We have some cantilever CLT panels. We have certainly a lot of cantilevered timber beams. And we also have some notching out of the CLT. I mean, they're not quite Mickey Mouse shaped, but they are there. All things that you wouldn't be easily capturing by hand if you were to check a panel by hand. And so certainly having TrueSoft as a tool was great, and that's what we've been using from the beginning. So it's not a simply supported beam calc, and even for schematic design, we had to have some form of finite element analysis. Looking a bit more at the that sort of localized typical bay model, I mean, we've used in our case a standard 200 thick panel of CLT, and that's what we have throughout the tower. But one could be interested in exposing some hardwood lamellas, for example, and on the underside, and you could have a different layer, and it's really great to have a tool that allows us to change those layers if we want to, and it doesn't need to be a specific CLT manufacturer. It can be any manufacturer, any properties. We and that's not illustrated in this slide, but we are, for example, talking to local Australian suppliers. The market is not huge there, but there are some suppliers, and they're using different species of timber. So while what you see on the screen is what you would get as typical European spruce for CLT, there might be some of the CLT which will be supplied locally and will have different capacities and stiffnesses. And it's great that we can integrate this into the same software. Right, so after changing or after setting up the properties of the panels and the geometry, we've run some analysis like you would do with any analysis software, getting some bending moment diagrams in both directions, which is what you see on the left. Getting some deflection plots, checking in this instance the deflection under a 1 kilonewton point load, which was required for a vibration check. On the bottom right is a mode shape for the first natural frequency, all done in the same software. And I'm not going to go in detail again about these, but it was really quick to check utilization of our panels, and especially the local stresses around those notches. And in this case, because the beams don't extend all the way to the edge of the CLT, understanding the peak moments and whether that would fail the CLT panel locally or not. You see on the left the stresses in the different lamellas of the timber, and then on the top right you see utilization, which extends from dark green, which is close to 0, to extends to some almost yellow green-ish, which in this instance was up to 75% utilization. And the bottom right image shows all the Eurocode checks that Stoyan presented earlier. And we've also applied this to our larger scale timber habitat model. This diagram shows, I guess, the process that we've gone through, but one thing that wasn't talked about earlier today was the fact that FEM Design allows a very quick panelization of any panel. So going from the first to the second image on that diagram, in a few clicks, you can define the typical panel width, and it would automatically break down your larger panels into a regular spacing of CLT panels. And this is quite important, actually, when you look at for example, weak axis bending and cases where your CLT extends further than the support, because the panelization means you've got a cut in your CLT and you don't have a moment continuity suddenly. Sometimes you don't even have a full shear continuity along these interfaces. The panelization is normally something that is done later in the process of the design by the timber manufacturers, because it depends on a lot of site logistics and more importantly, it depends on transportation. But we know, for example, in Europe, that panels come typically at 2.4 meters width. It can be slightly larger or sometimes slightly less. So it's good to have an idea from the start and to do that panelization earlier in the design process, at least to get a feel for what could work. And then going around the loop clockwise, we've checked the panel utilization and gone into the detailed CADs from Eurocode 5 to see that everything was okay. And I think that's all I have for today, and unless there are any questions, but that's. I mean, one thing you may ask is why we've used the Eurocode 5, even though the project is in Australia. That's probably an obvious question. And the answer is there is certainly some timber industry and a code for Australian design, but it's not very advanced, and it's commonly accepted to use Eurocode 5, which is much more advanced. And there's been a lot more research done in Germany, in Austria, and in the rest of Europe, and using Eurocode 5 is acceptable. And also, FEM design unfortunately doesn't yet do design to Australian standards, so we've had to stick to Eurocode.
Mm-hmm. How do you feel, Eloi, is this CLT construction industry going? Is there a lot of tendency for more projects in this using this type of material, or are you working on other projects or have any upcoming projects in CLT or timber?
Yeah, definitely. I think many structural engineering companies are pushing for the use of timber generally, and CLT is an efficient way of using timber for floors. But yes, there is definitely a push in the industry for pushing clients to use CLT and timber generally. It's sometimes not necessarily more expensive. There's a better feel, but most importantly, it's got a better carbon footprint, and that should be everyone's target now. So yes, whenever we can, we are advising for CLT, and often it is becoming more and more successful, and we're managing to use CLT on more and more projects. So more to come, for sure. Yes.
Great. Thank you, Eloi. Thank you for joining us and taking the time to present this really interesting project.
No problem. Thank you.
Please go to strusoft.com, and here you can read more about the Atlassian project, and you can read more about FEM design in general and the CLT module. If you go to Strusoft and choose FEM design, here we can see all of the design modules, including the timber design and the CLT module. And you can read more information about it. And there we have also a YouTube channel where you can see different topics treated in short videos. To get started with FEM design, you just go to Get Started Now and apply for a trial license here. You just fill out this form and
just a second, Flavio. We submit. Don't see a screen.
Oh, I'm sorry.
Now it's better.
Thank you, Sven. Yes. On strusoft.com under FEM design, you can select FEM design here. And you can see all the design modules. And to get a trial license, you can just click on Get Started Now and choose the trial license and fill out this form. And you will will submit your application for trial license, and we will process that, of course. So thank you one more time, everybody, for attending. Thank you, Stoyan, and thank you, Eloi. Hope to see you soon, and happy modeling in FemDesign. Have a great rest of the day.
Thanks. Bye, everyone. Thank you.
Thank you, everyone. Bye.